Okay, part two, how to prove. So I'll talk about three different proving things, three different proofs, direct proofs, if you're trying to disprove something, and contradictions. So firstly, direct proofs. Uh, Basically, you're going to have something like A implies B. This is what you want to prove. You want to show that this is true. Um, so you want to say, all right, suppose A is true and show that B is true. Okay. So I'll give an example of the first sort of common mistake that people make, which is supposing the result holds before you've proven that it holds. So a concrete example, from the assignment, there's a question like this. That I can't remember the exact question, but basically you have to prove that there exists Q such that I don't know, n equals 4q minus 1 or n equals 4q plus 1. Something like this, right? So what you want to do is find some integer q. No, don't even call it q, right? You just want to find an integer and then show that it satisfies the required properties and therefore it is q, so you've shown that q exists. But a common mistake that people made was declaring that Q exists before showing that it exists. Actually, I just remember the question, so I could probably just do the whole thing now. All right. Suppose n is odd. Show that there exists Q and Z such that n equals 4q minus 1 or n equals 4q plus 1. Right? So given some odd number n, we want to find a q so that n equals 4q minus 1 or n equals 4q plus 1. So first I'll give an example of a proof which is wrong, and I'll say why it's wrong, and then I'll give an example of a proof which is correct. Okay. So, let n be odd, right? Then n equals sort of 2m plus 1 for some m in integers. Let n equal 4q minus 1 or 4q plus 1, then 4q minus 1 equals 2m plus 1, so 4q equals 2m plus 2, so 4q equals 2m plus 1, so 2q equals m plus 1, so q equals m plus 1 over 2. Right? And then you can do a similar thing. If it's 4q plus 1, you're going to end up with something like q equals probably just m over 2, maybe. And now someone would say, alright, so if m is odd, then this is an integer, so q is equal to this. If m is even, then this is an integer, so q is equal to that. So why is this wrong? Well, I guess there are two important reasons why this is wrong. The first one, which is the reason I showed this proof, is because here you're saying let n be equal to this or this, right? You're declaring that there exists q so that n is equal to 4q minus 1 or 4q plus 1. When the whole proof is, you're trying to prove that there exists a q, and here you're saying that there exists a q, right? And you just pulled it out of thin air. So you don't know that you can write n in this form, so you can't do this, right? And the second thing, which is the problem, is simply because you've got an or here, right? N equals something or something. It's not it's not very clean to say that n equals two things. You want n to be equal to just one thing, so it's not ideal. Alright, and an example of something which is correct. So you don't want to mention Q right until you've shown that it exists. So that should be the first moment that Q is mentioned, right? And that's a direct proof showing that Q exists. So, okay, if m is an integer, either m is odd or m is even, right? So, case 1, m is even. Then m equals 2p for some integer p. Ooh, screen went dark. Oh no, alright. So then m equals 2p. So then n equals 2 times 2p plus 1, which is equal to 4p plus 1. And case 2, m is odd. Then m equals 2s plus 1. For some s in the integers, choose s to be equal to, I don't know, like k minus 1, where k is an integer, right? You can find an integer k so that s equals k minus 1. And then n equals 2 times 2 times k minus 1 plus 1 plus 1. Rearrange that, and it ends up being 4k minus 1, probably. Alright, so once you've done this, you can say, alright, in this case, set q equal to k, and in this case, it's equal to p, and then you're done, right? And now you've shown that q exists. You haven't had to suppose that it exists by talking about it, but you've reached the conclusion that it exists because you've found integers that satisfy exactly the properties that you want them to satisfy. Alright. Okay, how to prove part 2, disproving something. So, disproving things is easy because all you need is one example that makes it false, right? So, let's say your statement is something like, okay, for all n in z, there exists m in, actually I'll make that n, for all n in n, there exists m in n, such that n m minus 3 is prime. Okay, so for every natural number n, you can find some other natural number so that nm minus 3 is prime. Suppose we're told to either prove this or disprove this. Okay, so if you wanted to prove this, right, then you need to find m for every single natural number, right? You need to find some constructive way of proving that there is m so that this is prime. That's if you want to do a direct proof, right? Which is hard, right? Because you've got infinitely many cases. You can't do anything with numbers. So, slight detour. There were a few people who would say something like, suppose you're trying to prove that this is true. They would say, alright, consider the example where n equals 5 and m equals 1. Then 5 times 1 minus 3 is 2, which is prime. So finding an example doesn't work because that doesn't prove that it's true for every n, right? All that does is prove it for one single n. So if you're trying to prove something, if you're trying to prove for all n and n, or for all something, you need to give a more general proof than an example. But now, if we want to find a counterexample, that's a lot easier, right? If you want to disprove, if you want to show this is not true, all you need is a single natural number where there is no n, right? As long as you can find a single natural number so that this is never prime, then you're done, right? It's a lot easier. So in this case, choose something like n equals, I don't know, like 12, and then you have 12m minus 3, which equals 3 times 4m minus 1. So now for every natural number m, this thing here, this is equal to, if m equals 1, it goes to 3, and then the next one is 7, 11, and so on. It's always 3 times some other natural number. It's composite, right? It's not prime because you've got, this is a composite number now. So we're done, right? All you need to do is say, hey, look, if n equals 12, there is no m, so this is prime. So if you want to disprove something, counterexamples are the way to go. Don't do anything general if all you need to do is find one single example. The easier the proof, the better, right? The easier the proof is, the easier it is for other people to follow it, the clearer your reasoning is, and so on. So always go for the easiest option. For disproving things, it's usually counterexamples. Cool. Okay, the last part of how to prove contradictions. Let's say you want to prove a statement like, basically something in the form A implies B, right? So you want to prove that if A, then B. So a contradiction is just, so you rearrange this with classical logic, and you have that the negation of, well, this is equivalent to negation of A and not B. So the negation of something, which is supposedly the same as the initial thing you started off with, right, is going to be basically just this, right? You want to prove this, right? You want to prove that A and not B is false, and that's the same as proving that if A is true, then B is true. So I think most people are fine with this. They understand this, but when they actually try to write a contradiction proof, they can not quite write this out here. You know? So an example could be Alright, if I am sufficiently hungry, I can eat a horse. So, if you wanted to prove this directly, right, if you want to prove it like this, you say, alright, part 1, suppose I am sufficiently hungry. Yeah, whatever. Then you have some sort of logical deduction, and eventually you reach the conclusion that I can eat a horse. Okay. So what about contradiction? You want to start off with this thing here, right? You want to start off with A and not B, and then eventually you want to show that it's false. So in this case, if A, right, if I am sufficiently hungry, then I can eat a horse. This is B, right? So for a contradiction, you want to start with, okay, suppose I am sufficiently hungry and I cannot eat a horse. Alright, so this here is literally A and not B, right? So if you're doing a proof by contradiction, at the top of your proof, right at the start, you should have something that looks like this. You should have A and not B. This should appear right at the start. And you can even add something like just forehead, in front of the suppose, you could write, with a view to contradiction. Right? So if you do that, then it shows whoever's reading your proof that the reason you're supposing that this thing is true, even if it's going to be false, is because you want to have a proof by contradiction, right? So proofs by contradiction are a bit backwards. They're weird. They're not very nice. So it's good for the reader to know that it's a contradiction before they start reading it. Otherwise, it's like, what's the point of this? So you start with that and literally write out A and not B. So a lot of people, if they're doing a contradiction proof, they will not add this at the start, right? And they would eventually reach a contradiction because they sort of implicitly supposed that this was the case. But it's a really unnatural thing to do. You don't really want to assume anything in maths. You should write everything explicitly. If you're doing a contradiction, literally write A and not B before you do anything in the proof. Yes. Okay, I missed out something important. There's a new addition to our how to proof list. Words. Sometimes someone might write something like this. The set of n in z such that n is not equal to 2q roll q in z. Alright. Something like that, right? So you look at this and you just go, ooh, what? It's gross. Symbols everywhere. In reality, this is just a set of odd numbers, right? So you could say, instead of saying s equals that, you could say s is the set of odd numbers. Alright, which of these is nicer to read? Top one or the second one? Basically, pretty much everyone would agree that this is a lot nicer. They're both just as explicit as each other. And if anything, words are better, right? Because this here, the word odd, it only has one meaning, right? In maths, at least. It's only got one specific meaning, which is that a number can be written in the form, n equals 2q plus 1 for some q in the integers. So we've created that terminology so that it can be used. So there's no point writing something like this and avoiding using words because it looks more mathsy or something. Because in reality, words make everything a lot clearer and easier to read, and the flow of your proof is going to be better. And basically, a word is worth 1,000 math symbols. So use words.